Great to be back and hope you enjoyed the previous videos. Now we are going to look deeper in algorithm and specifically searching algorithms. Searching is something very important in computers. Think about Google search and other searching programs. Now, let's first have a look what searching algorithms are about. Like I said, searching problems are very common. We try to find the spelling of a word. The list of words is, for example, the dictionary, and we want to find that word as fast as possible. When you remember using a dictionary, you will see that in the dictionary, the words are ordered alphabetically. So you can already go straight to a specific part in the dictionary where you can find that word and make your search more, let's say, efficient. Now, that dictionary and other elements exist. Now, it is also possible that the list that you have is not ordered. So the dictionary has been ordered, which makes it for you very interesting. But just imagine if this was not the case. Now, when we have an unordered list, we basically have to look through the elements step by step. So when we want to find a number in a list or a word in a list, it's not a problem when that list is not ordered. It only makes it a little bit more complex. Now, when we're looking at searching algorithms, we're looking at different algorithms. And in the case here, in this part of the course, we will be looking at the linear search and the binary search algorithms. And I will explain both of them, what the difference between them is. Later in this chapter, we will be looking deeper into the number of calculations we have to do, because the time it takes to find the value is related to the number of calculations that have to be done. The less calculations, the faster the algorithm finishes the task. Your search algorithms is in fact an algorithm that tries to find the element in a list, going through every element of the list up to the last element, but stops whenever the element is found. So we don't have to go to the end of the list. If we're lucky, we have the element in the beginning of the list. When we are not lucky, it will be the last element. Typically, if I look for something, for me, it's always the last element. So I think it's kind of fate for something I probably did wrong in a previous life. But whenever I have to look for something, it's always the last element. Now, in reality, it is not always like that, but you will see that when we have this algorithm, we can do it a lot faster. Now, when we have the same element that appears multiple times in a set, then the algorithm will stop when it finds the first element. So once we find the first element that is equal to the search element, then it will stop. It's also possible that we have a search algorithm where we want to find all the identical elements. For example, dates of birth would be something that can occur more than once in a list. But let's just say that we have a list with unique numbers or unique data, and we try to find one element in that list. Now, the result of this is the position of that element in the list. And of course, it is possible that we do a search, and sometimes we do a search and we get a result back not found. So it's also possible that because of some conditions, the value that we want to find is not part of the list. And in that case, we get a result, element not found. Now, the linear search algorithm is very useful when we have a list of numbers or data that is not ordered. Once it is ordered, we don't have that problem. We can do it in a different way because we can find these elements without any problems. Now we go through the list one by one and until we find the element or not. Now let's first have a look at the pseudocode for the linear search algorithm. Again, we start with a procedure name, which is called linear search over a set of numbers A1 till AN. So like I said before, it's good to know that we have these elements in the program because we can find what we did wrong very easily when we are debugging the program. We start at position 1, so it's the first position. So I is equal to 1. Then we have a while loop. A while loop is a loop which continues to compare the value with the next value, and it goes to the next value as long as we didn't find that value that we are looking for. Now, once we find that value, we put the location there. So we found it at the end, we find the location, and when we didn't find the element, so if we don't find the element, we put the location equal to 0. And the return, the output, is the location, either the position in the set or the 0 indicating that we didn't find the number. So the pseudocode are easy, and we can now continue with the binary search algorithm. Now, binary search algorithms try to find elements in an ordered list, and ordered means from the smallest to the largest or the largest to the smallest. Now, you have to be careful when you're ordering. Some elements are ordered differently. For example, the American or the English alphabet has a different order than, for example, the Czech alphabet. So depending on what language you're working in, you can find certain differences. A thing I always do is when I put a reference for a file, and I put a file name that I want to find, let's say, the latest improvement, the latest update from one of the programs that I did or the documents I did, I put a date string at the end of the name of the file. Now, what happens sometimes? When you put there, typically like we think every day, like in Europe we say date, month, year. In the US or UK you may say month, date, and year. But let's say we put it first, day, month, and year. If we order it like that, it will not be ordering in a logical order, because it will look at the numbers, it will not look at the date as a number, and in that case we have to take some precautions. And if I want to order them, let's say, according to the date, I can add, for example, the year, the month, and the day, and then we have a nice ordering sequence of our files. Now you have to be careful how you order things, and let's say we have to look at that. Now, when we have the numbers, typically it's from largest to smallest, smallest to largest. Numbers are okay. When we have strings of letters like words, we typically order alphabetically, or also what we call lexicographic. Now, like I said, when we look at the file names, be careful, because the file names consider the letters that you put in there, or the numbers that you put in there better, as letters. And then the ordering is a little bit different. So you have to be careful. You have to understand how the ordering is really done. Now, what we do here in the binary search algorithm, we have a list, and we split that list in the middle. So we say in the middle, it's an ordered list, so we know the number in the middle, that all the numbers at the left are lower than that number in the middle, and at the right, they're higher than that number in the middle. And what we do, first of all, we look at the center value. Now, if we are equal, our number is equal to the center value, our problem is solved. If our number is smaller, we split the string in two parts, and we only consider the left part. When the number is higher than the middle value, we take the right part. And now we continue this until we find the element we are looking for in the data list. And this is a very interesting thing, because this algorithm, the fact that we have the binary search algorithm, it makes our search a lot faster, but there are better algorithms than this. Let's look for the letter I in the alphabet. So we have I in the alphabet, we have A till Z. I use the English alphabet, and the letter I is bold. Now in the middle we have two possibilities. We have M and N. So normally we will see the procedure will take the lower letter, so it would take N, but basically we can have M or N in this case. Now we see that the letter I is smaller than M. So basically we consider the left subset to continue our search. And that left subset, I included M here, but it's not really necessary, is in fact A, B, C, D, E, F, G, H, I, J, K, L, and M. And G is the new middle. Now here again, I look to the left or to the right, and I see that I is larger than G. So now I look at the right subset, and I continue here. So now I continue with this subset, and the middle is between J and K, and I find basically that the last division, I find the letter I between H and J. And that's basically the principle of the binary search algorithm. Now let's have a look at the binary code, the binary search algorithm, the pseudocode. And what we see, we have a procedure here which I call binary search from A1 to AN, an ordered interval. I is equal to 1 is the left endpoint of the interval. J is equal to N is the right endpoint of the interval. So we have from 1 till N, the start and the ending. While I is smaller than J, we say that the midpoint is the floor of I plus J divided by 2. So when we take that element, and we will do it in a calculation later on, that we find that middle value. Now we compare the value I'm searching with the value at the position M. Now if A is larger than M, then I look at I is M plus 1. So basically this is a new definition of the left endpoint of the new interval. Else J is equal to M. It means that I have a new endpoint, right endpoint of the interval. So in the first case, I have the numbers between A1 up to AM plus 1. And on the other case, I have the numbers, I have for A larger than AM, the first point is M plus 1. So that's the new starting of the interval up till N. And in the case that A is smaller than AM, then I find J, which is in fact the new end of the interval. So I take the midpoint as the new end of the interval. Now, if A is larger than AI, then the location is I, otherwise the location is 0. So we can find those elements that we have, and of course the endpoint of this procedure returns the location either I or 0. I, when we find the location, then we have it, then we put there the location of the value A. If we didn't find the number A, we say it's 0, which means that we don't have the location. Let's consider now the binary search algorithm on another example. We look at the array that we have here with the numbers 15, 17, 20, 30, 31, 32, 33, 34, 40, and 45. and we are looking for the number 40. Okay, it's a very small list here, so we know that the number 40 is in the position 8. We have 10 numbers, so basically, what do we have to do? First, we have to calculate the middle of the array based on the low and high element. So we have the position 0 is the lowest element, and position 9 gives the highest element. And then we can calculate the middle value by using the formula. The middle value is equal to the low plus the floor of high minus low divided by 2. So basically we're going to round down. Low is 0, high is 9, low is 0 divided by 2. So we have the floor of 9 halves is the floor of 4.5. So basically we can say that the middle value, the middle position is position 4 with a value of 31. And that's what we are going to do now. So we have the middle element of the array, 31, which is now in red. And now we have to say 40 is larger than the value in position 4. So now we consider the right subarray from m plus 1 till n. m plus 1 is 4 plus 1 is 5 till 9. So the new subarray is 32, 33, 34, 40, and 45. The next step is we have to find the new middle value. So the new middle value is now the low value, which is 5, plus the floor of the high minus the low is 9 minus 5 divided by 2. So we have 5 plus 4 divided by 2. 4 divided by 2 is 2, so the floor is 2. So we find now that the middle value is 7. And we look again at the next element. We see that A7 is 34. So 34 is in the red. And we know that A7 is smaller than 40, or 40 is larger than 35. So we have a new subarray from A8 till A9. So we only have 2 elements in this new subarray. So basically we have the mid plus 1, 7 plus 1 is 8, and the high value remains unchanged. Now we apply again the calculation of the middle value, and we find that low plus high, floor of high minus low divided by 2 is 8, the low is 8, plus 9 minus 8 divided by 2 is 8 plus the floor of 0.5, which is basically 0. So the new position is 8. And here we see in the position A8, this is 40. So now we found the value and the algorithm ends here. Now it is clear when we look at this, when we have an ordered set of values, it is clear that the linear search is slower than the binary search algorithm. So once we have an ordered list, the binary search algorithm is very interesting to use. So that was a first introduction into some algorithms which are quite important when we are dealing with algorithms. Searching is very important, and in the next session we will be looking at another very important problem, which is sorting algorithms. You saw that when we were looking at this problem, we assumed that that list was sorted. Now, there is no magic that sorts these algorithms. We could count on Harry Potter or perhaps Hermione to sort these numbers, but basically it doesn't work like that. We have to find an algorithm to sort a list, and later we also will have to look at algorithms that will add elements to an already sorted list, because those lists are constantly growing and we don't want to keep on sorting all the time. So that was it about the linear search and the binary search. I will see you in our next presentation about sorting algorithms. You're doing a great job. Thank you and bye-bye.